Okay, it's 12 o'clock, so I will start. This is BK Brain Korea 21 New Frontier Seminar this semester, and today's speaker is Dr. Hee-Jeong Kim. She got a PhD in the KAIST, and her major is structural materials, and she's going to talk about designing sustainable construction materials for carbon neutral by 2050. So it looks like very interesting topic. And as you may know, she will work as an assistant professor in the University of Arizona from early next year. So how long will this seminar will be?
It will be about 40 minutes.
Hmm?
40 minutes.
Okay, so 40 minutes. So once she finish, we can have a discussion session shortly. So please welcome Dr. Hee-Jeong Kim.
Thanks for introducing me, and thanks for being here. Today, I would like to give a seminar about designing sustainable construction materials for carbon neutrality by 2050. Can you hear me? 잘 들리시나요?
소리가
네.
들리긴 들리는데 저한테는 굉장히 잘 들리진 않아요. 네.
아, 그래요? 제가
네.
다시 한번
네.
마이크를
들리긴 들리.
네, 한번 하겠습니다. Before I start my presentation, I will introduce myself and research. I received an undergraduate degree at KAIST and pursued a master's and PhD degree program from the same school in the Department of Civil and Environmental Engineering. During my graduate research, I used the various byproducts as a supplementary cementitious material instead of the massive CO2 emitter, which is cement. And I made sustainable concrete with those materials and evaluated durability characteristics with the multi-scale analysis. I joined the MIT in 2019 and conducted research for cement hydration mechanism for developing sustainable 3D printed materials. These are my research topics, and all my research can be divided into 3 big categories. First is carbon neutral construction material. Second is sustainable construction material. And lastly, 3D printing construction material. Today, the seminar will discuss how construction material research can play a significant role to avoid a climate disaster. First, I will explain why carbon neutrality and CCUS technology are important. Then I would like to explain about sustainable aspect by designing low CO2 concrete. Lastly, I will explain why 3D concrete printing technology is important and how it is also related to climate disaster. I will start with carbon capture utilization and storage CCUS technology in cementitious material first. We are all talking about climate change, and the reason is we are facing a big challenge, global warming, and the future is on the line. And even for last week, a prominent UN climate summit, COP26, was held in Glasgow. Every year, global CO2 emission is rapidly increasing because of industrial activity, and CO2 gas stays in the atmosphere for hundreds of years. Carbon dioxide can absorb heat and trap into the atmosphere, and it contributes to temperature rising. As the graph on the right shows, the global keeps rising every year, and global warming is a real problem we are facing. Then how can we avoid climate disaster? To solve this problem, about 200 countries agreed in 2015 Paris Agreement. They tried to keep temperature rises well below 1.5 Celsius degree to avoid the worst impacts of climate change. And experts say that to achieve this, net zero must be reached by 2050. And at last week's summit, several international agreements came out. China agreed to phase down coal starting in 2026, and more than 100 countries agreed to do more cut down greenhouse gases, including methane. And they vowed to end deforestation by 2030. And lastly, India, the world's third biggest emitter of greenhouse gases, had pledged to achieve net zero carbon emissions by 2070. And President Biden has a plan for clean energy revolution and environmental justice. Here are the plans for his climate actions. First, President Biden has signed for rejoining the International Paris Agreement this January, and this new administration is aiming for achieving net zero emissions by 2050. Also, Department of Energy already announces $100 million funds for clean energy solutions for supporting President Biden's climate agenda. CCUS technology and reimagining the carbon neutral construction material are key topics of the advanced research project focused on climate ARPA-C that President Biden will establish. Back to the point, carbon neutrality by 2050 is one of the solutions for avoiding climate disaster. The dictionary meaning of carbon neutrality is to make real emissions zero by taking corresponding measures to offset carbon emissions. There are two main ways to absorb carbon dioxide emitted from industrial activities. First is forest resources, and the other one is carbon capture, storage, and utilization. And why by 2050? If the temperature of the Earth rises more than 2 degrees Celsius from now, there will be a level of natural disaster that humans cannot afford. But if we limit the average temperature rise to 1.5 degrees Celsius, the risk is greatly reduced. Thus, carbon neutrality should be achieved by 2050. To achieve the carbon neutrality by 2050, carbon capture storage (CCS) technology is essential. CCS requires 5 techniques: CO2 capture, compression, transportation of CO2, storage, and leakage monitoring. However, CCS still have several issues. First, CCS technology limitations exist, and second, those CCS technologies are expensive and costly. Third, they have hazards during the CO2 capturing and transportation. Lastly, CO2 leakage problems. Here are the examples of CO2 transport hazards. CO2 gas requires low temperature and high pressures, and it leads to corrosion or fracture of the transport pipe. Another problem of CCS is leakage. If the stored CO2 underground leaks, it can contaminate the drinking water, which is only 3% of total water, and also cause severe earthquakes. Mineral carbonation is a way to overcome the limitations of the previous methods. Mineral carbonation technology belongs to the CCS field because it solidifies carbon dioxide. However, CO2 captured mineral can be used, so it can also belong to the field of CCU, carbon capture utilization, that reduces or utilizes carbon dioxide. In conclusion, mineral carbonation became the most important technology in CCUS. Mineral carbonation has the highest capacity of carbon storage and have safer and longer storage time than other carbon storage methods. And also it is one of the best examples of CCUS. And it is also can be applied to a variety of materials that have high contents of calcium byproducts, for example, coal ash, cement waste, etc. And mineral carbonation studies have been carried out with high temperatures and high concentration to accelerate the carbonation reaction. Therefore, using CCUS technology in concrete materials will help achieve carbon neutrality. Since concrete is used extensively around the world, even a small amount of CO2 capture and storage could have a tremendous impact. CCUS requires a regionally tailored approach because of the limitation of CCS technology mentioned earlier. If you see the power generation resources in the southwest where Arizona is located, coal is the largest power generation source, and Arizona has the largest nuclear power plant in the United States. So we need to think about how we can tailor CCUS technology in coal-fired power plants and nuclear power plants in Arizona. And we also need to think about how we can tailor CCUS technology in South Korea too. Here is the CCUS technology utilization possibilities in coal-fired power plants. One of the CO2 utilization strategies is using CO2 gas from coal-fired power plants to mineral carbonize industrial byproducts in concrete minerals. I used coal ash mineral carbonation material in this research. Various types of industrial byproducts can be used as mineral carbonation materials. Most of byproducts include calcium, silica, alumina sources. Industrial byproducts with a lot of calcium sources are suitable for mineral carbonation. If calcium oxide in byproducts meet water, it changes into calcium hydroxide, and calcium hydroxide leads to an active mineral carbonation. So I used the two types of coal ash in my research to confirm that it can be used as a mineral carbonation material. The first ash is circulated fluidized bed combustion type coal-fired power plant ash, which is a CFBC ash, and the other one is pulverized core type fired power plant ash, PC ash. Usually CFBC ash contains high amount of Ca because during the coal combustion process, they put limestone through a desulfurization. As you can see in the chemical composition table, it has higher amount of CaO contents than PCA ash. Both core ashes are carbonated with the actual CO2 concentration of the power plant. SEM images confirm that calcites, which are calcium carbonate, are produced during the mineral carbonation in CFBC, which has abundant calcium minerals. And also from XRD results, lime and calcium-bearing minerals in CFBC also participated in mineral carbonation. That stable carbonated ash can be used as an aggregate or additive in concrete. Now I want to explain how to design sustainable and low CO2 concrete. We can say that concrete is the most destructive materials on Earth because concrete is second most used material after water in the world. All concrete manufacturing processes have huge environmental impacts. For example, cement manufacturing, water consumption, and aggregate mining all have environmental impacts. But the most climate affecting of them is cement making. Cement manufacturing contributes about 8% of all man-made CO2 emissions. Because when we manufacture the cement, we heat together limestone and clay at a temperature of 1450 Celsius degree. But in fact, most of the CO2 emissions do not come from the heating, but from the breaking down of the limestone, which is calcium carbonate into calcium oxide and calcium dioxide. Why sustainability is important? Because we are facing pollution. Then how can we make CO2 less hardened material? I propose that we can use supplementary cementitious material, hereinafter referred as SCMs, instead of cement. SCMs are usually core combustion residues, which are divided into fly ash and bottom ash, and blast furnace slag, which is byproducts of a steelmaking process. If we can use those byproducts instead of cement, we can make sustainable and CO2 less hardened material because of few reasons. Firstly, the amount of byproducts has been increasing because of increased industrial activity. And secondly, most of those SCMs are buried as landfill, which causes a lot of environmental and economic problems. As a result, there is a need for recycling of SCMs. I will explain the different chemical reactions in PC binder, blended PC binder, alkali activated material binder. In Portland cement PC mixture, the hydration reaction occurs when cement and water mix it, and it produces the main hydration product, CSH, calcium silicate hydrate, and calcium hydroxide. In blended PC, which is SCMs, added at cement, SCMs will react chemically with water. Also, pozzolanic reaction, which is chemical reaction with hydrated cement, leads to additional strength-bearing phases and densifies the microstructure of cement. In alkali activated material, we use only SCMs, but cement, which emit CO2. SCMs are alkali activated material, such as they are using alkali hydroxide and alkali silicates, and produce hardened material with less CO2. SCMs make the alkali activated materials with abundant aluminosilicate sources. And for those reasons, the main chemical phase is aluminosilicate gel. The chemical structure is similar to gel-like, but alkali activated material has amorphous or semi-crystalline phases. The history of alkali activated cement is short. Metakaolin has been used for making geopolymer first, and fly ash has been used recently started. SCMs can be used as precursor. Whichever precursor is used, it gains strength and results in a hardened material at the end. However, what gives the strength differs according to the precursor, because the alkali activation products of a precursor determine physical chemical characteristics. I want to show the different durability characteristics of a Portland cement and alkali activated material. The durability of alkali activated material is comparable or better for the majority of modes of deterioration. Especially alkali activated material will perform well at extremely chemical aggressive environments. Cement is used in long-term storage and disposal of radioactive waste. However, OPC has long-term storage limitations, so new advanced materials binder is needed. The high durability material geopolymer can be used instead of cement. Geopolymer matrix consists of aluminosilicate gel structure and exhibit excellent resistance to acid, and also has a greater immobilization ability of radioactive material than cement. Research on high-performance binder materials that against various deterioration factors is needed. I will explain alkali activated slag, one of the high-performance binder among variable alkali activated materials. According to the literature, alkali activated slag materials are stronger against sulfate and chloride damage than conventional cement. And also, alkali activated materials are low in permeability and good at resisting fire. And the durability of alkali activated slag is also comparable to or better than OPC durability. However, alkali activated was replaced the alkali activated slag to improve this weakness. because CFBC ash contains high amounts of CaO, which acts an expensive additive. In this study, not only fly ash, but also bottom ash used. Many studies about the recycling core combustion residue focused on fly ash, not bottom ash, due to the rough texture, various sizes, and high porosity. The left graph shows the dimensional stability, which is important for durability and strength of the concrete. Fly ash and bottom ash, which are SEM's substituted samples, had better dimensional stability than the control sample, which is alkali activated slag. And if we see the pore size distribution of different hardened mixtures on the right graph, SEM substituted samples shows higher amounts of smaller pores than the PCE samples. Thus, it shows the densification of the microstructure by using SEMs. In addition to those mechanical properties, it is possible to manufacture construction materials that are resistant to chemical deterioration, such as carbonation by incorporating SEMs. As for the carbonation reaction in the matrix, carbonation reaction can degrade the strength of concrete by decomposing CSH, which is the main hydrate of the cement matrix. Because CSH is primarily responsible for strength in cement-based materials, however, the main product of alkali-activated CFBC ash slag is CNASH, calcium sodium aluminosilicate hydrates. So the carbonation behavior differs from CSH carbonation, and carbonation products led to a dense alkali-activated slag matrix. To sum up, SEMS can be used as a highly durable and sustainable construction material. Lastly, I would like to explain why 3D printing concrete technology is important and how it is also related to climate disaster. 3D concrete printing technology strategically extrudes and sprays concrete materials. Unlike conventional construction materials, 3D concrete printing enables atypical buildings with a high degree of freedom. And the simplified construction process makes economical construction possible. The production of structures and non-structures through 3D concrete printing technology also can contribute to the reduction of carbon dioxide emissions by development of a sustainable and low CO2 3D printing construction materials. 3D concrete printing requires high fluidity of the material for ease of operation. However, using high flow materials leads to performance degradations, such as plastic shrinkage due to the spreading and separation of the materials, generation of voids, and reduction of interlayer adhesion. Besides, the structure is at risk of collapse when printed horizontally and curved surface structures because of lack of support. Last, the most common 3D concrete printing problem is the occurrence of the cold joints. The material properties and the printing speed is important for not making any cold joints. So understanding the cement hydration kinetics can help determine hardening properties, which is a significant factor in 3D printing. 3D printing construction materials have many challenges, and there are different kinds of problems for each scale. In material scale, setting characteristics of concrete is challenging, and for structure scale, structure optimization design is important, and sustainability should be considered in construction scale. Thus, understanding cement hydration is needed. Research on the early cement hydration mechanism is the key to understanding the cement matrix's physicochemical properties. Sustainable, durable construction material. The functionality, materials, structures, and processes of 3D printed concrete all related to each other, so that the optimal 3D concrete printing material conditions can be derived through multi-scale analysis and multi-scale optimization. The optimization of 3D concrete printing for each scale is described as shown in the following figure. In this context, 3D concrete printing research goals can differ for each scale. For material scale, characterization, understanding the cement hydration process with chemical characteristics, and for structure scale, mechanical characteristics of the concrete, and long-term observation and durability tests on the printed buildings can be a research goal for a construction scale. This research includes fundamental characterization of fresh concrete mixes, a full understanding of the workability and structural integrity of the designs, and physical properties of final materials. The left figure shows the multi-scale computational modeling techniques and multi-scale experimental characterization to understand the cement hydration mechanism. Cement is mainly consists of calcium silicates and calcium aluminates. So I will explain the cement hydration process. It is easy to use when concrete is fluid during its induction phase, and it hardens through hydration processes into a strong material. As concrete, the strength develops during the setting stage. Despite the importance of this stage, factors and mechanisms that influence and determine the chemomechanical changes in cement matrices in the early stages remain unclear. Therefore, many researchers are trying to understand early cement hydration mechanism with various experimental techniques. SEM, TEM, CT scan are used for imaging of early cement hydration. And for tracking of chemical changes in early stage hydration, also studied with the various experiments such as XRD, TGDTA, and FTIR. However, those analysis methods are invasive and samples are damaged by the sample preparation processes, such as crushing, heating, vacuuming, etc. The non-invasive method of Raman spectroscopy can overcome these disadvantages. Therefore, Raman spectroscopy is optimal for tracking the early stage of cement paste transformation. I use the Raman spectroscopy method to obtain the result with spatially and temporally resolved early cement hydration process and identifying cement hydration products. And the goal of this study is understanding the dynamics of the early stage cement hydration process and understanding the structure of a CSH. Here are Raman spectra of calcium hydroxide and silicate phases. And the Raman mapping image of calcium hydroxide and each silicate phases is shown in the right figure. C3S alite and C2S petalite are main calcium silicate clinkers in cement, and it accounts about 80% of cement, and their main hydration product is CSH and CH. With Raman mapping results, it can be confirmed that C3S is consumed by hydration reaction and produces calcium hydroxide as time goes by. But C2S petalite has no significant changes because it contributes to the finer strength of the concrete. One of the advantages of Raman spectroscopy is its capability of identifying different hydrated phases. These OH are found in 3,000 to 3700 over centimeter, and it can be categorized into 4 types: free water, bound water, CaOH, and SiOH. In this study, we focused on OH symmetry stretching peaks and CaOH containing phases. OH bonds can be found in many different components in cementitious materials. The OH profile of CH, DCH, which is a disordered CH, CSH, are compared here. CH and CSH both have OH bonds, but they have different profiles, for example, peak position and peak width. By decomposing peak profile, we can identify local environments of OH bonds. So this is animated CaOH peak position and width. So we plotted peak position and peak width of a CaOH, and we visualize how the peak properties changes over time. From this analysis, we discovered new phase, which is amorphous calcium hydroxide or disordered CH. And we found that this phase is worked as precursor of calcium hydroxide before the setting process occurs. From CSH spectra has 3 different OH bonds, which are bound water, CaOH, and SiOH. We can speculate that CSH would have broad bound water peak and a slightly wider OH peak at a similar peak position as CH with a right shoulder. And researchers have suggested many CSH models, and our Raman spectrum supports Gartner's CSH model. Not only OH phases, but also different sulfate phases can be differentiated with Raman spectrum. And the Raman mapping image shows that a large amount of ettringite is already produced at 1 hour of hydration. Ettringite formation is related to the setting properties of cement and densifying the cement matrix structure. So I will explain the future research at University of Arizona. I worked on understanding cement hydration kinetics on material scale at MIT, and I would like to expand my research into designing sustainable and low CO2 concrete with a multi-scale approach, including structure and construction scale at, at University of Arizona. Also, I've been working on multi-scale experimental characterization, but I would like to expand to multi-scale computational modeling with collaboration in the future. I also want to develop high-performance concrete for extreme engineering. Cement can be used for geologic CO2 sequestration and well decommissioning, and also for engineered barriers in nuclear waste repositories. For well decommissioning, cement is used to support steel casting and protect it from corrosion, and as a permanent seal for decommissioned wells. So it requires high temperature and high pressure bearing binder. And cement is used in advanced materials to isolate radioactive hazards because cement has been in contact with water for millennia. However, there are limitations exist. For well cement usages, the carbonation leads to CSH scale dissolution and forming a porous structure and allowing the ingress of chemicals, which potentially cause steel corrosion. And for radioactive nuclei fixation, calcium leaching causing the porous structure, and it causes leaching of radioactive materials to the groundwater. Thus, durability is essential and key performance for extreme environments. Alkali activated material can be used as perfect material for extreme engineering. I want to develop alkali active material with local industrial byproducts. Lastly, I want to develop concrete with combining cement hydration, 3D printing concrete, and geopolymer research. Why do we think about living on Mars or the moon? Like, if carbon neutrality by 2050 fails and climate disaster occurs, this can be a backup plan. And those planets are closest to the Earth, and they have the most similar environments. And if we want to build a habitat in space, we need a special cement for construction. Because environments of Earth and the moon are different. The temperature of the moon ranges from minus 150 degrees Celsius to 100, like minus 150 degrees Celsius to plus 150 degrees Celsius. And cement require water for setting the phases, but it is difficult to get water in space. For this reason, astronauts keep conducting experiments for future space construction. Therefore, further studies on cement hydration is needed. Cement hardens through a cement hydration process in setting. And space concrete has different chemomechanical characteristics because no gravity in space. Therefore, there are many topics to study. Scientists developed the concrete with astronauts' urine and moon dust. This is creative research, but I would like to develop perfect mixed design for space concrete in the future. Thank you for listening. And if you're interested in working in University of Arizona, please mail me, and my email address is cement, cement at mit.edu. Thank you again.
Okay, thank you very much for the interesting presentation. I guess that is a part of your job talk. Anyone has any questions? I think we have a graduate student from different majors, so environmental engineering student may also have some questions. No question. So because this is very similar with my research interest and my research directions. So I'm not going to ask about some questions on your research, but you got your bachelor degree and master degree and PhD degree in South Korea, KAIST, but you got assistant professorship that is a tenure track, right? Tenure track assistant professorship in the State University in the United States. So how was that process, and can you share your experience with our students?
First of all, I was a little bit surprised that like in United States, they're preparing for the like faculty positions from the PhD degree program. So after they graduate from PhD degree, they can actually start new position like as a faculty member. So I thought I was not ready for the position, but like some of the students who recently graduated from the graduate school, they're trying to prepare the materials for the faculty position. So I decided why not, and that's the reason why I applied for the position. And for me, it was taking a while to preparing for the teaching statement and the research statement. And personally, I think doing a TA at your university would be really helpful for your future position if you're interested in working in this area.
Because fresh PhD student in the US, they get immediate faculty position in the US because your school was MIT. It's very PhD students very limited, and also there are many universities in the United States, teaching school, research school, and so on. And I also agree that the carbon neutrality 2050 is something that we really pay attention to, and we need to go in that direction. So I also hope that we can continue to collaborate each other, and wish you best luck in your first career in the United States as a professor.
Thank you so much for your comment.
Any questions? So if there is no question, and thank you very much, Hee-Jeong Kim, Dr. Hee-Jeong Kim, and then stop our New Frontier seminar today. Thank you very much.